let me ask you a question that might sound a little weird. What actually makes a triangle a triangle? Well, it turns out there are these strict, invisible rules that decide whether a shape can even exist. Today, we're diving into that hidden logic, triangle inequalities. And trust me, this isn't just boring textbook stuff. These are the fundamental rules that dictate how space and shape really work. Okay, let's jump right in with a puzzle. Just look at this triangle for a second. If you have one side that's really, really long, what do you think that does to the angle that's sitting right across from it? Does it make it the biggest angle, the smallest, or does it not really matter? This one simple question is actually the key to our first huge rule. And that leads us right into our first section, which I like to call a triangle's golden rule. It's all about the unbreakable connection between how long a side is and how big its opposite angle is. Here it is, the official rule, laid out as Theorem 3. It's pretty straightforward. If one side of a triangle is longer than another side, then the angle across from that longer side is guaranteed to be bigger than the angle across from the shorter side. It's a direct link. Bigger side, bigger opposite angle. Simple as that. But, in geometry, you can't just say something is true because it looks right. You've got to prove it. So here's our puzzle. We're given this triangle where we know side AC is longer than side AB. Our mission is to prove without a doubt that the angle opposite AC, that's angle B, is bigger than the angle opposite AB, which is angle C. The first move here is just so clever. To crack this, we're going to make a really strategic cut. We'll find a point, let's call it D, on that long side AC, and we'll place it so that the new length AD is exactly the same as our shorter side, AB. This one little move creates a special new triangle inside our big one, and that's the key. And boom! Here's where the magic happens. Because we made that cut, we've just created a brand new, smaller triangle, triangle ABD, that's isosceles. And what's the one thing we know about isosceles triangles? The angles opposite the equal sides are also equal. This gives us two equal angles to play with, and that's the piece of information that unlocks this whole proof. So the bottom line is, we just proved the golden rule. It's not a hunch, it's a geometric fact. When you make one side of a triangle longer, think of it like a support beam in a bridge. The angle opposite that beam has to open up wider to accommodate it. They're locked together. Naturally, this gets you thinking, okay, so a longer side means a bigger angle, but does it work the other way? Does a bigger angle also guarantee a longer side? What happens if we just flip that logic on its head? And the answer is yes, it absolutely works both ways. This is what we call the converse of the theorem. And the logic is perfectly reversible. If you can see that one angle is clearly bigger than another, you can be 100% certain that the side sitting across from it is the longest one in the triangle. They're really just two sides of the same coin. All right, let's build on that. We're going to go from the rules inside the triangle to the world around it. And this next principle is something you already know deep down because it's all about finding the shortest path from point A to point B. This is Theorem 5. And it basically just confirms something you do in real life without even thinking about it. If you want to get from that point O to the line AB in the absolute shortest way possible, you're not going to walk at a weird angle, right? No way. You're going to go straight down, making a perfect 90-degree angle. That perpendicular line is the undisputed champion of shortness. Any other path you take is going to be longer. Period. Okay, now for probably the most famous inequality rule of them all. This is the one that answers a very real, practical question. If I just hand you 3 sticks of different lengths, can you always snap them together to form a triangle? Well, this section is the ultimate construction test. And here is the law that governs it all, the triangle inequality theorem. It sounds a little fancy, but the idea is incredibly simple. For any triangle to actually exist, you have to be able to take any two sides, add their lengths together, and that total has to be longer than the one side you left out. And this means you can't just check it once. You have to run the test 3 separate times to be sure. Side A plus side B has to be bigger than C. Side B plus side C has to be bigger than A. And side A plus side C has to be bigger than B. If even one of those tests fails, you do not have a triangle. It's a deal breaker. Let's make this super real for a second. Imagine you've got 3 pieces of wood. Their lengths are 2 feet, 3 feet, and 6 feet. Can you lay those down on the ground and make them connect into a closed triangle? According to our rule, something's about to go wrong here. And here's exactly why. Let's run the numbers. We take the 2 shorter sides, the 2 and the 3, and add them up. What do you get? 5. Okay, now is 5 greater than the last side, which is 6? Nope, not even close. The 2 shorter sides just aren't long enough to meet. You can picture it. Lay the 6-foot piece down and try to hinge the other 2 on the ends. They just can't reach each other. You physically cannot build it. So we've got our rules in our toolbox now. We know bigger sides mean bigger opposite angles, and we know that any 2 sides have to team up to be longer than the third. Now let's put these tools to work and see if we can solve some more complex geometry puzzles. Whoa, okay, take a look at this problem. We've got a quadrilateral, a 4-sided shape. We're told that side AB is the shortest side, and side DC is the longest. The challenge is to prove that angle A is greater than angle C. But wait a minute, all of our rules are for triangles. This isn't a triangle, so how do we even begin? Well, the secret, and this is true for so many geometry problems, is that if you don't have the shape you want, you make it yourself. We're just going to draw one single straight line, a diagonal from A to C. And just like that, we've broken one complicated problem into 2 simple ones. Now we have 2 triangles, and we know exactly how to work with those. So here's our game plan. It's a simple 3-step process. First, we slice the shape. Second, we use our side versus angle golden rule on each of the new triangles. Since we know which sides are longer and shorter, we can figure out which angles are bigger. And finally, we just add our findings together from both triangles and boom, we've solved the original puzzle. It's such an elegant strategy. When you really get down to it, all of these cool tricks come back to a few fundamental truths. This idea that 2 sides must be longer than the third, it's not just a rule you memorize for a test. It's really part of the basic fabric of our 2-dimensional world. It's just how space works. It's so easy to just dismiss these as simple classroom rules, but these exact inequalities are the foundation for everything from engineers designing structurally sound bridges to the GPS satellites that triangulate your phone's position on Earth. The logic of the triangle is literally everywhere. It really makes you wonder, doesn't it? What other simple hidden rules like these are out there, quietly shaping the world all around us?